Okay, well, it's a pleasure to be here. I'm going to spend just a minute on a little background. I'm coming at this community somewhat obliquely. For the last 20 years, starting in 2005, I've been working on developing techniques for high throughput volume electron microscopy using serial section transmission electron microscopy, culminating in the publication last year of the FlyWire connectome, which is shown on this first slide. This is the 50 biggest cells in the fly brain. But in 2018, my lab published the underlying EM volume as a resource for the community as an open data set. We saw it actually in Norman's first images that he showed. So the volume was used widely for many purposes. And it was, just to give you a sense of scale, 7,000 serial sections, 21 million individual EM images, 110 terabytes of raw EM data. So and this was work done from 2011 to 2016 on acquisition, the next few years in alignment and early segmentation efforts and publication. So I'll just make a couple points about the TEM data. Back in the day, we had the so-called isotropy wars, where anisotropic voxels were thought to be highly inferior, isotropic voxels were superior. And for those, in case anyone doesn't know, that just means our voxels were 4 by 4 by 40 nanometers. Like in FibSEM, you'll get, depending on your acquisition speeds and parameters, maybe 4 nanometers on each edge cubic voxels, or more typically 8 to 10 when you try to encompass large enough volumes to map neuronal circuits. But this just shows, an example of, well, yeah, okay, on the z-axis of the TEM data, you may be somewhat lower resolution, but for favorable structures in the XY, you're actually at higher. So this just shows a reconstructed neuron in the fly brain, and then in the middle panel, you have sort of the resolution that we imaged the whole brain at, but you can go in and zoom in on these data and see plenty of material. And actually on the right, this is a little bit beyond just a digital zoom. You can actually go and reacquire that same spot if you're interested in further detail, it's a sample preserving method. So that's the first worked example, but in a very different regime. And then the second one is I've had a sort of long-standing back burner interest in protists, and I'm delighted to be at EMBL Heidelberg as of a month ago for a 10-month visiting sabbatical fellowship in Yannick Schwab's laboratory, an interaction that actually initiated at the volumeEM conference in Barcelona this past summer. So it's sort of been interesting to become acquainted with this smaller world. And I don't have the data ready yet, but colleagues at Genelia actually did some 4 nanometer FibSEM. And so now, these older 2D views of the beautiful ultrastructure of the cortex of these ciliated protists, we now I'm processing in Dragonfly. And I'm not ready to show all this yet, but I actually am starting to have a feel for both the past work, extreme large volumes, and now this much smaller world and sort of workstation-based analysis. So that's 4 minutes of talking, and then the last minute I want to make the most important point, which is this trend towards larger volumes over time. So in my graduate work, we did a 10 terabyte volume of mouse visual cortex. This is the complete fly brain. The y-axis is a log scale of synapses. And, if we look, what's happened is this high throughput volume EM in the pursuit of connectomics, in my view, biased, has trickled down or into the volume EM community that we're seeing here. And it's taken, 10, 15 years for that to sort of disseminate out, some of these tools and approaches and so on. Now, that is biased. It's not, I'm sure it's not all from connectomics-based data generation efforts and processing efforts, but I think it's fair to say, serial block phase scanning EM was motivated by connectomics, and improvements in FibSEM were motivated by connectomics. And so we have that in the lower left. And then and these days you can get away with small commercial efforts, a little bit of open source, et cetera. Oh, the green is not showing up. Well, I'm sorry about that. On the upper right is the world of like whole fly brains, and that you can only deal with these enormous dedicated teams, millions of dollars over 5, 10, 15-year time spans. And so the point I'm trying to get to in 5.5 minutes now, there's this missing middle, right? And so that's the point of view I kind of want to inflict on you, or maybe we can talk about in the working groups, that I think that both the number of smaller volumes and increasingly large volumes need to be handled by, I would like to see open source software. Commercial alternatives like Scalable Minds and others are emerging to handle this middle ground of volume, throughput, processing size, acquisition, processing, segmentation, analysis. But we need to get there as a community. And so I hope that this CCP volumeEM effort can think about how to achieve scale. And there are many worked examples that one can reuse and leverage. And so just to motivate this in a teeny bit of time, current volumeEM can do these monolithic slabs, 3 by 2 millimeters, petabyte on the left, right? But you can also embed lots of small samples. So now we have 77 200 micron cubes, and you can do about 5 of those slabs a year. So you're talking hundreds of 200 micron cube samples that a dedicated high throughput facility could generate. And so I think one way or another, this is coming in the next 5 to 10 years into this world. You're just going to get much greater flows of data if you want them. I think most people will. And so I think this is a great opportunity to get ready for that. Thanks, and sorry I went